Welcome. This is Dr. Morton, and this is class day 6. We're going to continue working on Logic Design Chapter 4. I will cover the homework. There is a homework due for in the next class day, and then this Saturday, the end of chapter quiz for Chapter 3 is due. So make sure you're ready to turn in the end of chapter quiz this Saturday by 11:59. So here is the here's the syllabus, and so you can see those things. All right. So I will work a little bit on. I'll talk a little bit about the homework that's due the next class day. Okay, here's the website, and if we scroll down here to the homework right here, and we pull that up for chapter 3, and I believe that's the right one. Let's see. Let me just triple check that. Okay, let me say a few things about the homework. So I do want you to write a truth table out for all 6 of the basic logic gates: AND, NAND, OR, NOR, exclusive OR, and exclusive NOR. I want you to take this schematic and convert it to NAND, 2 layers of NAND, and you can do that with the alternative symbols, or if you want, you can reduce it to an equation and solve and transform the equation. But I haven't really showed you how to do that yet, so probably better to use the graphical technique. And then describe what a functionally complete set of logic gates is in a few sentences, or one sentence. Really, it's pretty straightforward. I've said that a number of times in the videos. And then this encoding thing. So I'd like you to figure out what that IEEE standard is for floating point numbers. You just have to Google that and figure it out. It's basically when we declare a float type or a double, that's covered by the IEEE 754 standard. And you don't have to spend a lot of time learning or anything. I just want you to be familiar with it. So it's really a pretty straightforward set of homework problems. All right. Yeah, that's probably good then. Okay. So let's we have looked at the book here, and so I'm not going to spend a lot of time doing that. We've covered. I think we've been through most of it. If you haven't looked at the video at the beginning of chapter 4, make sure you do that, and it's right here. You just click on that, and make sure you're familiar with all these terms, and that should keep you in good stead. So we're actually a little bit ahead right now, but I do want to go. I do want to go back through and do some example problems on how we convert from SOP to POS and POS to SOP. Now, when we do this conversion, the first thing you want to do is look at an expression and see if you can simplify it, and then you want to look at our 3 simplification theorems. There are really 4, but like I said, we're going to leave this consensus theorem till later. If you want to look at that and learn that and use that, you're welcome to do that, but it makes more sense when we get to K-maps. And so we can combine terms, xy plus xy prime equals x, or the quantity x plus y times the quantity x plus y prime equals x. And then we can eliminate a literal. So x plus x prime y equals x plus y, and x times the quantity x prime plus y is just xy. And then we can eliminate a term. If we have an xy term and an x term, the xy term is superfluous, we can get rid of it. Same here. All right, and then once we get those things, then we have to think about using the distributive laws, either the first distributive law, C1, or the second distributive law, C2, or the multiplying and factoring theorem, C3. And usually, when we're looking for the first distributive law, we're typically going from SOP to POS. And when we're typically using the second distributive law, a lot of times RDM and F theorem, we're going the other direction. but we do use all the theorems to go both directions. So, but your probably first thought when you're going from SOP to POS should be the first distributive law, and it probably should not be your first thought when you're going the other direction. Okay, let's do some examples. Okay, so we've already worked that one. So what I will do, let's see. Yeah, so let me I want to do a couple of proofs first, and then we'll work some problems, and hopefully that'll fix everything up for you. All right. So so the second distributive law, if you remember that, actually let's do that real quick. So the second distributive law is x plus yz equals the quantity x plus y times the quantity x plus z. Okay, sorry, it's a bad parenthesis. Okay, so how do we prove it? We prove it by generating a truth table with all the variables in it. Well, how many variables are there? There are 3 variables, x, y, and z. So we're going to have 8 rows, and then we're going to have a whole bunch of output functions. We'll have this as an output function, we'll have that as an output function, we'll have that as an output function. The x already exists as a column, so we don't really have to generate an output function. But then we'll have x plus yz, the left-hand side, as an output function, and we'll have these 2 columns ANDed together as an output function. And what we'll show is that if these are exactly equal for every single combination of our 3 variables x, y, and z, so all 8 rows, then we know it proves the function. All right? Okay. So if you look at this truth table, here we go. So we have an x row here and a yz row here. So this is y ANDed with z. So 0 ANDed with 0, 0. 0 with 1 is 0. 1 with 0, 0. But 1 and 1 are 1. 0 and 0, 0. 0 and 1 are 0. 1 and 0 are 0. And 1 and 1 are 1. So we have 2 rows where y ANDed with z gives us a 1. And all the rest are 0. Now here we have x or yz. Well, the first four rows x is 0, so it just depends on yz. So we get a 1 there. But here we have 1 or 0, so we get a 1. 1 or 0, so we get a 1. 1 or 0, so we get a 1. And 1 or 1, so we get a 1. Now let's look at the right-hand side. So this is the first term in the right-hand side, and this is the other term. So x plus r, x or y. So x or y, so they're both 0, 1, 1, and all 1s. So 0, 0, 1, 1, 1, 1, 1. And then x plus z, or x or z. So x and z, they're both 0, so that's 0. But 0 and 1, that's 1. 0 and 0 is 0, and 0 and 1 is 1. And then all the rest of them are 1s. The rest, all 4. Now, if you look at these 2 rows, and we're going to AND them together and put them here. So 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. But 1 and 1 are 1, 1 and 1 are 1, and so forth. And now we compare our 2 green columns, the left-hand side to the right-hand side. And if those 2 columns match, if these 2 columns match, then we know that we've proven our function. And it turns out for every possible value of x, y, and z, this column, this green column, and this green column are exactly the same. So that proves the function. All right? Yeah. So that's good. And then we do have another proof here. And this is the multiplying and factoring theorem. And we do the same thing here. So if we go down here and we write that out, remember the multiplying and factoring theorem is x prime y plus xz equals x prime, well, and remember we do these little connecting things, and we do this little connecting thing. So that's x prime plus z quantity times x plus y. Now you can move this prime. If instead of putting the prime here, you put the prime there, then you take it off of here and you put it over there. It doesn't really matter where you put the prime as long as you keep it straight. Okay, So what we're going to do, we're going to generate this, and then OR them together for the left-hand side. We're going to generate this, and AND them together for our right-hand side. And let's see what we get. All right. So we get here, this is X and Y. So 0 and 0 is 0, 0 and 0 is 0, 0 and 1 is 0, 0 and 1 is 0, 0 and, let's see, did I screw up here? X and Y, 0 and 1 is 0, 1, 2, 3, 4, 0, 0, 1, 1. Yeah, and 0, 1, that should be, yeah, that should be a 1. Oh my goodness gracious. It's truly amazing. Okay, well anyway, let me fix that. Okay, took a little bit, but I fixed this. It's amazing. I hate it when I discover mistakes, but there are some. All right, so anyway, so you can see, so this is X and Y. So these are all going to be zeros, and then this will be 0, this will be 0, but 2 1s at the bottom because they're both 1. This is X prime, or Z. So the first 4 would be 1s over here, but the Z would only be 1 here and here. The bottom 4 would be zeros for X, so they're going to all be zeros. So it's 0, 1, 0, 1, and then 0, 0, 0, 0. Okay, and then we're going to take these two and OR them together. 0 ORed with 0 gives us 0. 0 ORed with 1 gives us 1. 0 ORed, and so no, I guess I can't, never mind. 0 ORed with 0 is 0. 0 ORed with 1 is 1. And that gives us, so 0, 0 is 0, 0, 0, 0. And then 1 ORed with 0 is 1, and 1 ORed with 0 is 1. So we basically have 1, 2, 3, 4 1s. 1, 2, 3, 4. Now we're going to do these. So in the inverse of X or Y, well, the first 4 would be 1s. The last 4 for X would be zeros. So we'll put 1s up here, and then the last 2 are 1 for Y. So this is what we get. And here's what we get for X or Z. The last 4 are 1s because X is 1 there, and then Z is 0, 1, 0, 1. So that's this column. Now we AND these columns together. So 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 0 ANDed with 0 with 1 is 0. 0 ANDed with 1 is 0. And 1 ANDed with 1 is 1. 1 ANDed with 1 is 1. So we get 0, 1, 0, 1, 0, 0, 1, 1. Exactly what we get for the left-hand side. So actually, I guess the right-hand side. So this is the left-hand side. Doesn't really matter. But the two sides are exactly equal for all possible values. All right. So we're going to be talking about our canonical forms. And those canonical forms then are SOP and POS. Now, turns out there also is a canonical form using exclusive ORs, and some logic design courses are actually built on that. But all our design tools and really our approach to design is really based on AND and the SOP POS forms. So that's why it's really not appropriate to make that the focus of the course. All right. So notice any logic expression can be put in one of these two forms. Every truth table can be represented in both an SOP and a POS form, which give you exactly equal results, but one of them may be able to be simplified to a much simpler solution than the other. Sometimes that's not true. Sometimes they simplify to the same level of simplification, or we sometimes refer to that as cost. So if you went out and bought the components, individual gates to make them, they would cost you the same, basically. Although, I mean, it's a construct. It's not a fact. You probably might pay a few cents more for one type of gate than the other. And these days, we don't make anything out of discrete gates, really, except for educational purposes or an occasional fixing a mistake or something. You can always convert from one form to the other. Now, I say, well, you may not be able to, but it's always possible to be done. I might not be able to either, although I'm probably closer to it than most of you will be. But it can be challenging sometimes, but it's doable. It should always be doable. These forms can be used to prove two sides equal, and I just did that basically. Well, I didn't use switching algebra to do it. I used a truth table, but you can also use switching algebra. They represent a hardware two-layer net. So one would be an AND/OR network where you have a bunch of input AND gates like this picture here, and one output OR gate. And the other would be an OR AND input where these, instead of AND gates, would be OR gates, and you'd have one output AND gate. You can have degenerative variables, which mean you just have a single term instead of a gate. Like you can have A, but you don't need a gate because there's no other term in that there's no other variable in that term. Single variable term. Okay. So remember that we call when we write SOP that we're using AND terms. We call those product terms. And we imply ANDing with multiplication, like this, A times C prime times D. That's an AND gate. We call OR sum terms, and we're implying ORing with addition. So A prime plus B plus D, that's an OR gate with three inputs, A prime, B, and D. And so that's why SOP is the summing, which is the output gate, of product terms. So the product terms are the AND gates, which are the input gates. The sum is the output OR gate. And the POS is the output AND gate, ANDing together all of our OR gate outputs, our sum terms. And here are the forms. And there's also shorthand notation. Let me show you that too. I think I may have mentioned that, but I want to touch base with that again. So if we have, let's say we have a truth table, and we use min terms, say 0, 3, 5, and 7 or something like that for three variables. So we could write that F equals the sum of the min terms, little m, 0, 3, 5, 7. And if we then wanted to write the max term side of that, we would say F equals the product of the max terms, capital M, and instead of 0, we don't use any of these, we would use 1, 2, 4, and 6, because that's where the zeros are. Here, for all these, F equals 1. For all these, F equals 0. So that would be 1, 2, 4, 6. And we call these forms the shorthand notation. Now, if we wrote out the expression, then we call it the expression. In this case, I can write the expression out. Let's say it's ABC. Those are our variables, three variables, right? So, because we have 8 rows here. So our expression would be the 0 term, which would be, so F equals, would be A prime, B prime, C prime. That's the 0 min term. Plus min term 3, which would be A prime, B, C. And then 5, which would be A, B prime, C. And 7, which is A, B, C. So those are our 1, 2, 3, 4 terms. 1, 2, 3, 4. Here we've written them out as an expression. And here we've written them out in the shorthand notation. I didn't write out the max terms, but it'd be the same idea. Max term 1 would be A plus B plus C prime. And max term 3 would be A plus B prime plus C prime. And max term 5 would be A prime plus B plus C prime. And max term 7 would be A prime plus B prime plus C prime. So that's written out. F equals. And notice these two would be exactly the same. They would equal each other. They would result to the same value for F for every possible combination of ABC. Okay. Sorry. All right. So let's go on here. So let me go through. So I talk about these level 1 problems, and we're going to cover these, and then I talk about these level 2 problems. This is more of a level 2. Maybe I'll type that in here and fix that. Sorry. Okay, So we're going to do these. The level 2 are pretty hard. The things I have on the test will probably not quite be at the level 2 level. All right. So let's go back to level 1 stuff. Yeah. Okay. So let's do this one. First one, a prime plus c times b plus a prime times d prime plus a prime. And we're going to convert that to SOP. So it's what form is it currently in? It's in a POS form. Now, this one usually does show up on a test, so you want to pay attention here. So let's look at how that might look. Okay. So let me transition. So I'll get rid of this. All right. Now, what I want to do then, so I'll copy that down. So it's a prime plus c. So let me do this. So I'm going to copy it down, but I'm going to switch these and put the a prime first in each case. Okay. So a prime plus c. So let's go ahead and do that so I don't forget. Times a prime plus b times a prime plus d prime. Yeah. Okay. Now, so I'm going to use what I call a corollary to the second distributive law. The second distributive law is just x plus yz equals the quantity x plus y times the quantity x plus z. But a corollary to that is x plus wyz equals x plus w times x plus y times x plus z. Notice we have wyz, so we have 3 terms over here. Here we have yz, we just have 2 terms. If you had wyz j or something, you'd have 4 terms, and the last one would be x plus j. All anded together, all multiplied together, if you will. All right, so that's what you get when you use this corollary. Well, let's look at this. Do you see anything that looks like this over here, this side? Yeah, obviously you have a prime plus c, a prime plus b, a prime plus d prime. So why can't we just write a prime plus b, c, d prime equals f? And in fact, we can. So that's the answer to the first one. All right, let's look at the next one. We have AB plus CD. Convert that to POS. Now, I asked the in-person class, how many terms do you think we'll get out of that? And most of them said 2, but it's actually 4. Interestingly enough, 4 terms. So let's look at those. All right. So that was AB plus CD. Really pretty simple. Now, the way we're going to do this, we're going to go, this is currently in SOP form, and we're going to POS. And I'm going to use the second distributive law. X plus yz equals x plus y quantity times x plus z. Same rule I used to solve this problem, only I'm not going to use that corollary. Okay, so I'm going to let this be x, and this be y, and this be z. So that's going to give me AB plus y quantity times AB plus z. Well, sorry, this should be C, and this should be D. Now, so let me rewrite that, because that's a little confusing. AB plus C quantity times AB plus D. Now, if you look at what's in the parentheses, that looks a whole lot like the first distributive law again, right? Doesn't that look a lot like that? C plus AB is like x plus yz. So I'll just apply it again, and I'll break this one down. And so I'm going to write over here. So that's going to be C plus A quantity times C plus B. And I do the same thing here with D being x and A and B being y and z again. And so I just get D plus A times D plus B. So that's my answer. 4 terms. 1, 2, 3, 4. And that's one of those basic conversions that you should do a couple times. Make sure you're comfortable with that. That also could appear. All right. Then we have something interesting. We have AB plus A prime. We have AB plus AC. Well, how many terms do you think we'll get from that? Well, some in the class guessed 4 again, but let's look at that. So up here we have AB plus CD, but now we're going to do, I'll move over here. Now we're going to do AB plus AC. Well, notice we've got an A in each term. That actually makes a big difference. Now we can use the first distributive law, our conversion 1, and we'll factor out the A. So we just A times B plus C, and we're done. That's now in POS form. That's in SOP form. We have a degenerative case of an individual variable there. All right. Now, let's look at AB plus A prime C. All right. So, maybe I'll change this out. AB plus A prime C. Now, can you think of any of our 3 conversion rules that look like this? That's right, the multiplying and factoring theorem. Looks a lot like it. Okay, so we're going to do the little funky thing here where we do this so we can get these connected correctly. And that's just going to equal then A plus C quantity times A prime plus B. Now we have to have an A and an A prime here. Now notice, students make this mistake all the time. Don't make this mistake. If you had something like A, B, C plus A prime, B prime, D, could you call that X and this X prime and write it out kind of like that? No, you can't. Now you can use A and A prime, or you could use the B and the B prime, but A, B, so if you take A, B and you invert it, what do you get? Well, you invert all the variables and you invert the and sign there. So you actually get A prime plus B prime. That is not the same as, this is not equal to AB. A prime, B prime. It's not equal to that. So you can't do this because this isn't true, not true. But you can use the A variable and do that. That's fine. A and A prime. Or you could even use the B variable and do B and B prime by themselves. But you can't do A, B, and A prime, B prime as inverses of each other because they're not. The inverse of AB is not A prime, B prime, but A prime plus B prime. All right. So let's do this one. We're going to use the well, we already did. So here's that. So notice we have 3 very similar functions here, where we have something, well, AB plus CD looks similar, AB plus AC, and AB plus A prime C, but we treat them entirely differently. And then finally, let's look at this one. And there are others we could look at. I'm just going to try and keep this relatively short. A, B prime, C prime plus A prime D plus AC prime. Okay, so that's pretty straightforward. So let's do that. So A, B prime, C prime plus A prime D plus AC prime. All right, so let's switch over here. Now, I copied it down here, okay? Now the first thing, we really want to try and simplify, if possible. So do you see any place where we might be able to simplify? Well, notice we could rewrite this A, C prime, B prime, and here we have an AC prime, here we have an AC prime. So using simplification theorem S3, we can totally drop that term. What is S3? X plus XY equals X. Where the X in this case is the AC prime, and Y is just B prime. So we can drop that term, and we're just left with the AC prime term. Now we have A prime D plus AC prime. We've already worked one just like this, so don't really need to. But again, multiplying and factoring, we take this with this, we take this with this, and we wind up with A plus D quantity times A prime plus C prime. All right, same thing we did up here. All right, I think now if we do one of these other more difficult problems, like this one, that we talked about at level 2, there are some other things here. So we should be able to factor this. So let's look at this. So the first thing we do, we notice there's an A in every term, so we rearrange it. ACD, AC prime D prime, A prime B prime D prime, A prime B C. And then when we do that, we'll factor the A out of the first two terms and the A prime out of the second two terms. So there we are. We get A times CD plus C prime D prime, and we get A prime times B prime D plus BC. Now notice inside here, we can use the multiplying and factoring theorem, and we can also use the multiplying and factoring theorem on the whole thing. So 3 applications of the multiplying and factoring theorem, just like we just now did. And so if we do it on the inside, the parentheses, we'll do it on this one with one application of the M&F, or C3, and then here with the other application of C3, and we get A times C plus D prime times C prime plus D, and A prime times B plus D times B prime plus C. And now we'll do it again on this whole thing using A and A prime here, and we'll get A prime plus C prime D prime times C prime plus D, and A plus B plus D times B prime plus C. Now, if you look at this, you can see that the first distributive law works great here, because now we have x plus yz in here, and again we have x plus yz, a different x of course, but x plus yz here. So we'll apply it once on this, we'll apply the second distributive law once on this side, once on this big term, and once on this big term. But note, our or sign now is gone, so we only have product terms over here now. Inside the parentheses we have ors, but the two main terms are product. Well, when we do that, we get A plus B prime plus C times A plus B plus D out of this bunch of stuff here, and here we get A prime plus C plus D prime times A prime plus C prime plus D. All right, so that's another example. And then we can go on down. Let me show you, this is another one. You can look through this. It's pretty much a level 2 one. Fair amount of things we have to do to make this work. And sadly, we couldn't simplify this at all. All right. But now here's some, also somewhat tricky. But I'm gonna look at these. Here we can actually simplify. And this is a bit of a crazy one. It illustrates the application of our simplification theorem 2 that is hard to see sometimes. And so let's look at that real quick. All right. Okay, I've written it down on the paper. Now notice we have 2 theorems we're going to use. The first theorem we're going to apply 2 times, and it's our simplification theorem 2, S2. And that says x plus x prime y equals x plus y. Well, so that's what we do. Using this, I can eliminate that x prime, and using this, I can eliminate that z prime. So now we're just left with xy plus y plus xz. Yeah. Sorry, I miswrote this. It is xy plus x prime yz plus yz. So I actually don't have an x term here. I have a y term there. I knew that was a mistake. All right. So anyway, yeah, I couldn't have done that if that had an x term anyhow. So yes. All right. So now I get xy plus y plus xy. Now notice I can use my S3 now, which is x plus xy equals x, because you can drop that whole term. Well, I have a y, and I have an xy and a zy, so I can drop this term and that term, and I just wind up with y. So that whole thing simplifies to y. That's pretty amazing. That is definitely a level 2 simplification. I wouldn't expect you to see that right off the bat, and it might be really tricky to be confident that that was correct. Okay, and some of these others are equally tricky. I think what I'm going to do at this point is I think I've covered most of what I wanted to cover, and I think at this point I'm going to look seriously at terminating the video, because I think in the beginning we did talk about we talked about the homework, so hopefully you've gotten some pointers on how to approach that. Be sure and turn that in by midnight, 11:59 tonight, and then the next class period, which actually turns out to be Wednesday this time, because we don't have class on Monday. That class period, I think that's when the homework assignment's due. My bad. And then the homework assignment's not due tonight. It's due then. But the end of chapter quiz, and to do the end of chapter quiz, you have to have the book. And it's due on Saturday. In fact, every Saturday there's at least one end of chapter quiz, and there are 3 Saturdays where there are 2 end of chapter quizzes that are due. You have the whole week to do them. You don't have to do them on Saturday. But it's just that you can do it on Saturday, all the way up to 11:59. All right. If you have any questions, let me know. Otherwise, hopefully this will kind of get you pointed, and hopefully I kept this a little bit shorter, just 36 minutes this time, so that's great. All right. We'll see you on, the next class period.